Sivan Aditya Datta, an undergraduate senior majoring in computer engineering from International Institute of Information Technology, Bhubaneswar, Odisha, and India. And the co-author of this paper, Sri Keshav Reddy, is also my friend. He's also an undergraduate senior majoring in computer engineering from the same institute. Uh, we we together worked on this idea of how would it be to analyze the complex signal as regression, using regression, how we can analyze complex signal and understand how it is working. So that's basic idea of this paper, where it has been originated from. So I would like to go into the topic. So for the people who are not from the machine learning background, I would like to give overview. I'll take it from basic level to where we have performed the original idea. So linear regression is a form of unsupervised machine learning algorithm, and the main part, or the soul of regression algorithms, is how we choose the hypothesis. And today the aim of the paper is also the same: how we choose the hypothesis so that we can effectively formulate features as well as get astonishing results as compared to simple neural networks or simple deep learning algorithms. Um, so if you look onto the slide, we have first considered linear regression. Therefore, we have taken a linear hypothesis of format y is equal to x plus b. First, this format is only taken for the interest of audience, so that they can understand easily. We can even add regularization terms so that that is the depth of it. But we have taken only for the basic idea. And the main goal of this linear regression is that to consider a hypothesis: y is the output variable, x is the input variable, and our goal is to, like, given a data set, we have to optimize a and b so that for that data set we are able to for the future data samples we can predict with least error. The parameters can be, of course, optimized using the gradient descent or stochastic gradient descent. It's a simple linear regression algorithm, so I would like to keep the optimization for gradient. I would stop it with gradient descent itself. The idea matters. We want to translate the idea, not the techniques what we can use. Yeah. Finally, the required parameters can be estimated after using gradient descent and stuff. So going on to polynomial regression, of course, the idea itself is translated. So the difference between linear regression and polynomial regression is that we choose a different hypothesis. We choose a non-linear relationship. For example, if there is a non-linear relationship between the output variable and the input variable, the goal of polynomial regression is to capture that. And polynomial regression generally deals with, of course, as the name suggests, it deals with polynomial in polynomial of x, or the input feature. One thing we would like to add over here for polynomial regression is that not only if we consider polynomial x, we can also take trigonometric features into account, so that we can translate the polynomial regression to somewhat known as trigonometric regression. Actually, this idea has already been there. We've just wanted to include it to specify the significance of the paper. So if we tweak the hypothesis for polynomial regression, again, y equal to x squared plus bx plus c is only is taken as an example. So if we add some d sin x and d cos x terms over here, so it would become a mixture of polynomial as well as trigonometric features. The importance of this hypothesis is that if a equation consider, or if an underlying relation between an output feature and an input feature has an extra term, that is a trigonometric relationship, of course it may not show for large x. This may not taken into account, because d and e are maybe small, and sin x and cos x always range from 0 and 1, so it may not show certain error or high error between the problem statements. But this becomes very effective when x ranges from 0 to 1. So that is really important. That is the idea we want to capture. From this itself, we have got an idea. So why don't we take certain hypothesis and see how it works for music signal regression, as shown over here. So if we can also take a pure trigonometric function And for trigonometric signals, we can have trigonometric functions over here. So if we just see on a particular data set, taken a polynomial, just like how it is shown y equal to ax square plus bx plus c. We have taken a polynomial in x square, both trigonometric and polynomial features. We have included both as a set case, actually, that is, so that we can show how it is working. So if it takes an example hypothesis as y equal to x square plus bx plus c, as well as plus d sin x plus e cos x, so a mixture of trigonometric and polynomial, and we take a sample data set. We have taken x from 0 to 100, and we have constructed our own data set, and we have performed the calculations with simple linear regression. Of course, linear regression cannot capture the polynomial hypothesis, but our desired output are shown in figure 2. We want to get something, our prediction should be something like figure 2. That is how it should work, but it's not working like that. And even if we take polynomial regression, the actual polynomial regression, it won't work like that, because we have taken the set case to be completely trigonometric, but not a polynomial term is present in there. So trigonometric features cannot be predicted with polynomial regression hypothesis already there. So if we look at figure 4, I think it almost looks similar, if not the same, as figure 2, the required predicted outputs. Figure 4 is what we have taken our hypothesis, like it includes only trigonometric terms. Excuse me. So somewhat, I think we can understand that choosing a right features or choosing right hypothesis for a particular problem statement can be proved to be useful instead of going for advanced cutting edge techniques of machine learning techniques, or it may be deep learning techniques. And so here we want to establish an idea. Till here, we want to establish the idea that instead of directly going and searching with advanced machine learning techniques, first we have to understand the application, and while choosing a right feature or a right hypothesis can show effective learning than the counterparts. Thereby, even we can have high accuracy even on low data sets. We don't need a huge vast amount of data sets, which can save our time as well as burden. So now now we go into trigonometric hypothesis. Why we have taken trigonometric hypothesis is that the general audio signal, what we have observed, is in the format of a cos omega t plus b sin omega t. So we have considered an audio signal. For example, for a case study, we have considered an audio signal of that format. And if we have also used simple neural networks, we don't want to go into depth and use all the deep learning algorithms out there. But if we compare simple neural networks with simple regression hypothesis, so the neural networks were unable to learn it pretty much. They couldn't learn it because the data set was also, we have given a low data set, so deep neural networks cannot work on low data sets, and a relation as a cos omega t plus b sin omega t. So this relation cannot be captured with low amount of data set. So formulation, yeah, that's what y equal to ax square plus bx plus c is. We wanted to work on that, and we worked on this hypothesis also using both. We've also used logarithm. In the paper, we have used exponential terms too, but here we have kept it simple so that for understanding purposes, we can see if we use even the exponential terms. Of course, figure 5 is something we have predicted using support vector regression. It doesn't seem to learn the relationships, because the desired outputs are as depicted in figure 6. That is what we wanted. We wanted to get a results as depicted in figure 6, but using support vector regression, we are unable to capture what is expected. So the error is also very high, as we can see. It's really humongous. But if you figure 7, of course, it's by using polynomial regression. But if we put emphasis on figure 8, this is what we have used. So tweaking hypothesis a little bit and including exponential as well as logarithmic terms. We don't know how whether exponential terms will be present or not, or logarithmic terms will be present or not. But if adding exponential and logarithmic features to the data set, it sure seems to be helpful over here. I think here by this stage we want to establish the idea that adding exponential or trigonometric features or experimenting with the data set and using a hypothesis to predict the output should be made as a necessary step. Then we can explore other algorithms. Then we can go to the algorithmic stage. Otherwise, it's not that effective. So till here we have concluded with like exponential and logarithmic and how it would be, only trigonometric how it would be. So we want to establish that much. Going further, what the actual hypothesis what we have considered for music signal analysis is as shown, like y is a sine 2 pi sine x plus phase. This is another type of generic equation that has been taken. We have searched a lot, so we have finally decided to go with a sine 2 pi sine x plus the phase angle. But it's really difficult to take only one equation, and for the entire of course the audio samples would be like, they would be sampled like in millions over a few seconds of audio. So it would be not correct to for entire length of audio to take only a single equation and perform this regression analysis. So what we have done is that we have divided this 800,000 samples of audio into 800 segments, and for each segment we have taken 20 such 20 such generic equations and added it together and dealt with each we have optimized each copy of the hypothesis given as shown on the screen. We have optimized it separately, dependent on each other for each segment, so that we can get desired output, because using only one copy of hypothesis and translating it to training it over 800,000 samples didn't yield the expected results. We also tried with numerous other concepts, numerous other ways, but it didn't work out. But this way of handling it proved to be helpful. And we even to add, which is not over here, to add, we've even changed how the gradient descent works, actually tweaked a little bit. We actually we did not actually optimize all the parameters in one go. We first tried to optimize one parameter for the segment, and then depending on that parameter we optimized other parameter and the final parameter. So it is like parameter by parameter training instead of all parameters update in one cycle or so. Finally, we would like to show this figure 9, which is desired audio, which we want to get it. But figure 10 is another way. Figure 10 is what we wanted to, we've done actually independent parameter training. As I've already explained, for the gradient descent, we did not update the parameters for each step in one go. First, we have update for the entire segment. We have first updated one parameter, and the second parameter is updated independently without relation to the first parameter, and third parameter is updated without any relation to second parameter, and so on. So if we see that, of course, the amplitudes are quite off, but we can see the pattern. The pattern is almost captured correctly. If we want, of course, the method what we have proposed is not that accurate in learning the audio signal. But what we wanted to try to propose here is that sometimes simple machine learning algorithms like regression algorithms, if we choose the hypothesis in a correct way, then I think we can even recognize the pattern. I think the pattern is almost captured correctly without regard to the amplitudes. So if we study this furthermore, then we can actually even be able to accurately predict the amplitudes also, thereby proving that we don't need any complex complex techniques on a simple data set. If we are able to understand data set clearly and are able to estimate how the hypothesis would look like, then we are pretty much it. We can pretty much understand what is needed and work on it. Figure 11 and figure 12 are other ways. This is figure 12 especially is dependent parameter training. That is doing gradient descent on second parameter, taking into account the first parameter and remaining parameters. So if we take into account, I think we are not getting that much of a desired result. It is somewhere diverging off from the main problem set or the idea. And figure 11 is another type of method that has been used. Even if we take an amplitude, the amplitude parameter is also taken into consideration. But if I think that is the disadvantage of this paper. Amplitudes are we cannot predict amplitudes with this method, but this method can be proved useful to predict, to optimize the frequency parameter as well as the phase parameter of the hypothesis. So pretty much this is pretty much the paper we have put forward, and we wanted to get this idea into the outside research world. Generally, what we have observed is that even complex tasks such as music signal predicting or music signal analysis is somewhat deemed to be like a complex application, and only complex algorithms and techniques can do that thing, and we cannot use certain simple machine learning, basic machine learning algorithms to accomplish those tasks. But deep learning has its own disadvantages. It cannot learn on simple data sets, and the architecture has to be varied, tweaked depending upon the application, and it has its own disadvantages. Whereas simple machine learning or statistical machine learning algorithms, if we are able to get some points right, then I think they should be the go-to algorithms. If not, they should be first experimented with, and then I think we have to experiment on the remaining algorithms. So that's what is paper all about. I think I would stop